Hi, this is Dr. Shoykot Munandar. Under Basic Physics course, we will discuss transmission of heat. This is the continuation of the previous lecture, that is also the transmission of heat, where we have discussed radiation, conduction, convection, what is thermal conductivity, then definition of thermal conductivity, its unit, dimension, etc. Now this transmission of heat falls under the unit 3 of diploma syllabus, basic physics, heat and thermodynamics. The name of the unit 3 is. Learning objective is to understand different modes of heat transmission, thermal conductivity, good conductor, insulator, and their use in daily life. Continuing from the previous lecture, we know what is thermal conductivity, its expression of conductivity, heat transferred. Now we will discuss when two bodies are in series, what will be the equivalent conductivity. Let us consider here two bodies having equal cross-sectional area A and their conductivities are K1 and K2. This body A, the end of this body is kept at a temperature of θ1 and the B its temperature is kept at θ2, where θ1 is hot, θ2 is cold, and heat is transmitting from this left end to the right end. So at the juncture it is maintaining a temperature of theta. This is a common temperature. Now the body A, its length is d1 and body B, its length is d2. That means the heat when flowing from end left to the right, for body A it is covering d1 distance and for body B it is covering d2 distance. So the amount of heat flowing per second through A is K1 A θ1 minus theta by d1. The amount of heat flowing per second through B is K2 A theta minus θ2 by d2. In the steady state, the rate of flow of heat is same through any cross section of both the slabs. Thus, for the first slab, slab A, Q by T, that means amount of heat flowing per second is equal to K1A θ1 minus theta by T1, and Q by T for the second slab, K2A theta minus θ2 by D2. This is for the slab B. Now solving this, we will get the common temperature theta, common temperature at the common surface theta is equal to K1 D2 θ1 plus K2 D1 θ2 by K1 D2 plus K2 D1. The rate of flow of heat through the composite slab as put in the value of theta here. Q by T is equal to K1, K2, A, theta 1 minus theta 2 by K1 D2 plus K2 D1. Now dividing the numerator and denominator by K1, K2, we will get Q by T is equal to A theta 1 minus theta 2 by D1 by K1 D2 by K2. Here if we divide K1 by K2, this becomes D2 by K2, this one becomes D1 by K1. Just we are changing the position, D1 by K1 plus D2 by K2. Now if K be the equivalent conductivity of the composite slab, then Q by T will be Ka theta 1 minus theta 2 by D1 plus D2. How? Let us come to this picture. Now consider this is this 2 becomes one slab. Now the width or length will be D1 plus D2. Cross section area will be A, and the equivalent conductivity is say K. Then from the definition of thermal conductivity, Q by T will be K A, temperature difference between hot to cold, theta 1 minus theta 2 by the width D becomes here D1 plus D2. So Q by T heat flowing per second is equal to K A theta 1 minus theta 2 by D1 plus D2. Now let us divide the numerator and denominator by K. So it becomes Q by T is equal to A theta 1 minus theta 2 by D1 plus D2 by K. Comparing this equation with the previous equation, this previous equation is this. So we can write this part is A theta 1 minus theta 2 is same for both, and this one is D1 plus K1, D1 by K1 plus D2 by K2. Here it becomes D1 plus D2 by K. So D1 plus D2 by K is equal to D1 by K1 plus D2 by K2. Now if the widths are same, that means D1 is equal to D2, then we can write this one is D1 plus 2D1 by again D1 by K1 plus D1 by K2. So this one becomes 2, dividing both sides by D1, 2 by K is equal to 1 by K1 plus 1 by K2. Thus the equivalent thermal conductivity becomes 2 K1 K2 by K1 plus K2. Thus when the two conducting slabs are in series, the equivalent conductivity becomes 2 by K is equal to 1 by K1 plus 1 by K2. When the two bodies are in parallel, here in this picture the slab A and B are in parallel. The heat is flowing from this left end to the right end. So suppose the body A having surface area A1 and the body B having surface area A2 exposed to the heat directly. K1 and K2 are the thermal conductivities of the body A and B respectively. Now this end of these two bodies, left end, it is maintaining temperature theta 1, this is the hot end, and the right end of the two bodies maintaining temperature theta 2, this is the cold end. and the width the heat crosses is d. Now consider for the initial case these two are having different widths. So amount of heat flowing per second through A will be Q1. Per second is Q1. That means Q1 is equal to K1 A1 theta 1 minus theta 2 by D1, where D1 is the, say we are considering initially D1 is the distance from this point to this point for the slab A. Amount of heat flowing per second through B, BQ2 is equal to its conductivity K2, its cross section area A2 and temperature difference theta 1 minus theta 2 by D2, where we are considering the distance the heat covering in the slab B2 is D2. Now total heat flowing through these two slabs per seconds, if we write it as Q is equal to Q1 plus Q2. Thus Q becomes K1 A1 theta 1 minus theta 2 by D1 plus K2 A2 theta 1 minus theta 2 by D2. Taking common theta 1 minus theta 2, we can write K1 A1 by D1 plus K2 A2 by D2. So this can be written in the form of summation theta 1 minus theta 2. If there are n number of slabs, we can write theta 1 minus theta 2 summation of I is equal to 1 to n Ki Ai by Di. Now we will consider the thickness of the slab is as d. That means the heat Q passing from this point where it is maintaining theta 1 to the point where it is maintaining temperature theta 2. The separation between these 2 points is d. Thus, if K be the equivalent conductivity of the composite slab, the amount of heat flowing per second will be Q is equal to K, the cross section area between these two, it's A1, this part is A1 and this part is A2, A1 plus A2 and K A1 plus A2 into temperature difference theta 1 minus theta 2 by the width that is covering from point theta 1 to theta 2 is d. So Q becomes K A1 plus A2 theta 1 minus theta 2 by d. Simplifying and comparing this equation with the previous equation, we can write, because this part is d1, this, if we write this d1 is as d and d2 is also d, because we are considering these two are equal. So k1 by a1 theta 1 minus theta 2 by d plus k2 a2 theta 1 minus theta 2 by d. So these two, this total heat Q will be same. So we can write by dividing both sides, by multiplying both sides with d. So this becomes k a1 plus a2 and dividing both sides by theta 1 minus theta 2 is equal to k a1 a2 is equal to k1 a1 plus k2 a2. Thus the equivalent conductivity K becomes k1 a1 plus k2 a2 by a1 plus a2, where k1 is the thermal conductivity of the slab A whose cross section area is A1, exposed cross section area is A1, and K2 be the thermal conductivity of the slab B whose exposed cross section area is A2. So K1 A1 by in plus K2 A2 by A1 plus A2. This is the equivalent thermal conductivity when the two slabs are in parallel. Now let us do some numerical problems. The problem is the air in a room is at 25 degrees centigrade and outside temperature is 0 degrees centigrade. The window of the room has an area of 2 meters square and thickness is 2 millimeter. Calculate the rate of loss of heat by conduction through window. Thermal conductivity for glass is 1 watt per meter degree. So the window is made of glass. So heat loss per second will be Q by T. Here the temperature difference, the two ends are 25 degrees centigrade and 0 degrees centigrade. So theta 1 minus theta 2 will be 25 degrees centigrade. It crossing a thickness of 2 millimeter. 2 millimeter means 2 into 10 to the power minus 3 meter. And the cross section area of the window is 2 meters square. That means A is equal to 2 meters square. So we know the quantity of heat Q that flows from hot area to cold area is given by Q is equal to Ka T1 minus T2 into small t is time by x. The rate of loss is Q by T. Q by T is equal to Ka T1 minus T2 by x. So Q by T is equal to, putting these values, Q by T is equal to, this K means thermal conductivity is given, thermal conductivity of glass is given 1 into A means 2 meter square into 25 minus 0 T1 minus T2 by its thickness x 2 into 10 to the power minus 3. This is meter. So calculating we will get 25 into 10 to the power 3 watt per second. So loss of heat will be 25 kilowatt per second. Now come to the next problem. One of the possible mechanisms of heat transfer in human body is conduction through body fat. Suppose that heat travels through 0.03 meter of fat in reaching the skin, which has the total surface area of 1.7 meter square and a temperature of 34 degrees centigrade. Find the amount of heat that reaches the skin in half an hour if the temperature of the body interior is maintained at the normal value 37 degrees centigrade. Thermal conductivity of body fat is K is equal to 0.2 joule per second meter degree centigrade. The formula of heat flow is Q is equal to Ka T1 minus T2 by T. Here K is supplied 0.2 joule per second meter degree centigrade. A is also supplied. A is total surface area is 1.7 meter square. T1 minus T2. The body temperature is 37 degrees centigrade and surface area is 34 degrees centigrade. So this becomes 3 degrees centigrade. Temperature T1 minus T2. Time T is half an hour. Half an hour means this is half an hour. Half an hour means 30 minutes into 60. That means 1800 seconds. And thickness is X. Thickness is, it is given, travels to 0.03 meter. So X is equal to 0.03 meter. Putting these values, Q becomes 0.2 into 1.7 into 37 minus 34 into 1800 by 0.03. So we will get the value of Q is equal to 6.1 into 10 to the power 4 joule. However, heat transfer via blood flow to the skin is more effective and has the added advantage that the body can vary the blood flow as needed. The temperatures at the ends of a bar are 95 degrees centigrade at warmer end and 37 degrees centigrade at cooler end. The length of the bar is 0.9 meter. What is the temperature at the point that is 0.3 meter from the cooler end of the bar? Now length of the bar is given, that is 0.9 meter. Temperature at the warmer end T1 is equal to 95 degrees centigrade. Temperature at the cooler end T2 is equal to 37 degrees centigrade. Distance from the cooler end D is equal to 0.3 meter. Let temperature at this point be T. Heat conducted in a time T past the point at a distance 0.3 meter from the cooler end of the bar is given by Q is equal to Ka T minus T2 by D into T, where K is the thermal conductivity of the bar. And we know this terms. T is the temperature at a distance D from the cooler end. Thus, from this formula we can write T is equal to T2 plus QD by Ka T. As the heat Q originates at the warmer end of the bar, there is no loss of heat to the sides of the bar we are considering. Q is equal to Ka T1 minus T2 into small t by X. Substituting these values from this one, we can write T is equal to T2 plus Ka T1 minus T2 into D by Ka into X. K will cancel out. T becomes T2 plus T1 minus T2 into D by X. Putting these values 37 degrees centigrade plus 95 minus 37, the temperature difference, into 0.3 by 9. So T becomes 56.3 degrees centigrade. Therefore, the temperature is less than halfway between the temperature at warmer and cooler end. The last problem, an aluminium bar of length 20 centimeter and cross-sectional area 6 square centimeter is placed over a copper bar of same length but of cross-sectional area 4 square centimeter to form a composite slab of parallel combination. The temperatures of the two ends of the combination are 80 degrees centigrade and 40 degrees centigrade. Find the amount of heat conducted through the combination per second in steady state. Thermal conductivities of aluminium and copper are 200 and 400 watt per meter Kelvin respectively. Now let us solve this one. We know the amount of heat conducted through the combination per second in steady state is equal to rate of flow of heat through the first body, that is aluminium, plus rate of flow of heat through the second body, that is copper. There is a typing mistake, this will be copper. So this rate of flow of heat through aluminium becomes K aluminium cross section area A aluminium theta 1 minus theta 2 by D plus K copper A copper theta 1 minus theta 2 by D. Now these are known, 200 into 6 into 10 to the power minus 4. The temperature difference is 40 degree. So this one is D. D is already given. 20 centimeter means 20 into 10 to the power minus 2 meter. And here this is also same, 20 to the power minus 2 meter. And K copper is equal to 400. 400 into 4 into 10 to the power minus 4. This is 4 cross section area into temperature difference is same 40. So after calculating, this amount of heat conducted to the combination per second becomes 56 joule per second.